Hello, everyone. Today's lecture, we will talk about the root locus. So this is a new topic. A quick recap before starting the root locus, which is basically what we did so far regarding to the stability. The previous two lectures were about Routh-Hurwitz stability. So in Routh-Hurwitz, we determine the range of K when we have a feedback. So basically, what we learned from Routh-Hurwitz basically assume there is a system, G of S, and the system, it can be stable or unstable, whatever the system is. But if we need to shift the poles, because as we know, any transfer function, it has a numerator and denominator. So the denominator, basically, the roots of the denominator are called poles. Then this is the open loop transfer function or the original system. So that's why sometimes we call it open loop transfer function. Then if we need to move the location of the poles, one of the things, as we discussed in the previous two lectures, is to do a closed loop. So the closed loop basically can shift the location of the poles. And that closed loop you can multiply by a constant is called K. So that's what we learned in the previous lecture. Then we say the pole's location can be changed. Location can be changed based on the value of K. And we discussed in the also again like last two lectures that the system, for example, like assume we have this type of systems, then basically the poles, when we change the value of K, these two poles we are moving, then down the road we end up having a poles located like this. So in this type or in this kind of the systems that we discussed the previous lectures, when we change the value of K, the poles has been shifted from one point to another by changing the value of K. Then we reached up or end up by a point where basically, for example, like here K is low, then increase K. We end up by a point to make the system unstable. So we would say that when you increase K, in that example, we shifted the poles toward the right half plane. Then when we shifted the poles until reaching to the point where is try to shift the poles here, where is the system will be marginally stable. After that, the system will be unstable. So in Routh-Hurwitz, we calculated the value of K. In Routh-Hurwitz, we can say the system is stable or unstable based on the value of K by looking at the denominator and see how much the value. So basically, you can say the closed loop transfer function is K over 1 plus K G of S, or G of S actually, K G of S over 1 plus K G of S. Then basically look at the roots or the characteristic equation. 1 plus K G of S equals 0. So our target, we used to do the table for Routh-Hurwitz as like the table, then make sure to find it. And when we used to look at the first column to make sure the system is stable or unstable by determining the range of K. That's what we used to do the previous lectures. So basically, the previous lectures, we said two important things. The first thing, the poles location can be changed by the changing of the value of K. And the second observation, that the value of K can, if you keep increasing it, it can lead to unstable system. Then, therefore, in order to determine the critical value or the maximum value, maximum allowable value, or the maximum value for K to keep the system stable, we need to use Routh-Hurwitz. Now, in today's topic, it will be root locus. So root locus, basically, we will discuss the location of k, or when we increase the value of k, what's the tendency of the pole to be changed or to be switched from one step to the other step. So basically, I would say the root locus is the performance of a control system, which is described in terms of the location of the roots of the characteristic equations in the S-plane. So a desired response of a closed loop control system can be achieved by adjusting the control gains. So the root locus is a method analysis and design of the control system. So we would say like the root locus plot is the graph of the locus of the roots as one system parameter is varied. So I would say, since we discussed, and when we increase the value of k, the tendency of the, like as I mentioned, we mentioned here the tendency of the poles to move from one part to the other parts, this will be like a root locus plot. So we'd like to plot from k equals 0 until k equal infinity. So we'd like to see where is the location of the pole, or the location of the pole, where it's going to move. Starting from k equals 0, when the pole, when the system at open loop transmission function, then after that try to move to change the value of k step by step until reaching the infinity. Then we realize that if we can do this plot, this will be the root locus plot. Here, let's have an example. Consider the unity feedback control system with this part. So basically, let's assume it is first order, where is g of s equal k over s plus 1. Then the closed loop transfer function will be g of s over 1 plus g of s, which is k over s plus 1 plus k. So the pole, it's actually located at -1, -k. This is the closed loop pole. While the open loop pole, which is located at s equal -1. Therefore, if k equals 0, what will happen to the pole? S equal to -1. However, if k start increasing, like let's assume k here, if it's k equals 0, then it will be -1. If k equal 0.5, it will be -1.5. If it is 1, it will be -2. If it's 2, -3. Then keep increasing it, like 15, it will be -16. Then let's assume k equal infinity. Then the pole, again, it is s equal -1, -k. Here is the pole. Then if it is negative, if k is equal infinity, then -1 minus infinity, it will be minus infinity. So as a result, if we need to plot them, then we can say here is, for example, like the we can say S-plane mode, or which is like the same thing that we used to do in pole 0 mapping. Basically, the original pole. Let me erase it here. I think this is the axis. The original pole, or the open loop pole, before doing the closed loop, it was located at -1. So here is j omega axis. This is s axis. Then it was located originally at -1. Then if you keep pushing at here is when k equals 0, I think here it's -1. Then keep pushing, -2, -3, -4, -6, -16, then until k equal infinity, -infinity. So as a result, we can see that the poles have the tendency to be moved to the left half plane, more deep. In the previous example, in the last lecture, last two lectures, when we mentioned that the poles can be moved to right half plane mode, or it can move to left half plane. So it depends on the nature of the system. In this type of the systems, it is not moving toward the right half plane. Therefore, this seals the system is stable no matter the value of k, if k between 0 to infinity. So our target when we are discussing root locus, we will discuss only positive values of k. Only positive values of k. We will not consider a negative values at all. So when we have a positive values of k, then the tendency tendency of moving of the poles will be, I can redraw it again, like pole here, here, keep moving until reaching to the negative infinity. So when k equals 0, it's at -1. When k equal infinity, it will be, the pole will be negative infinity. So if we try to connect these points together, this yields to a graph. So this graph, I'll put here the arrow. This graph, this is the root locus. Root locus for this first order system. Okay, so in this type of the systems, again, we start from the pole itself, open loop pole, then it goes toward the negative infinity. That's the nature of this example. So again, the root locus is this plot. It's actually just discussing or start to see how is the systems changing by changing the values of k. So the root locus is the path of the roots or the path of the poles of the, so the roots of the characteristic equation or the path of the poles, closed loop or the open loop pole, I said closed loop poles, traced out by the S plane as system parameters varies from 0 to infinity. Again, keep in mind here, we will assume k varies between 0 to infinity. Then we would like to see if the system, can the system be unstable, or can the system, the poles moving to right half plane or not? Then that's also what we will discuss in root locus. So how to sketch the root locus? Assume we have this system, which is closed loop system. After doing the closed loop, it will be written as k over s, s plus 1, s plus 10, s plus 20, all of them plus k. Then when we do this, by changing the values of k to find the poles, actually this can be, when we have a higher order systems, it can be difficult to do by changing the possibilities, doing different possibilities of k. Therefore, it requires us to find a suitable method to find, to do the plots instead of doing substituting the values of k by and doing trial and error. However, if we have a small system, or if we have, I mean, like for example, first order system, we can choose all of the possible values of k manually by computing, changing the parameters of k from 0.51 until reaching the infinity. So it's easy because the poles can be found -1 minus k. Then that will be easy. However, for higher order systems, it will be infeasible for us. So therefore, we need to find a better way to do the root locus other than doing trial and error and computing different values of k. So construction of root locus. So finding the roots of the characteristic equation higher than 3, this will be computer solutions. I mean, we can do first order system, we can find the roots, we can find the roots, second order systems. For third orders, it's not easy, but we can find it. However, if it is more than third order, it will be very difficult for us, I mean, to find it manually. Therefore, we need to use computer solution by trying different errors, or we can use simple method. So a simple method, which is called the root locus method, a simple method for finding the roots of the characteristic equation has been developed by Evans, and he used we used it a lot in control engineering. So Evans has he has that method that help us in how to do the root locus. So this method is called root locus method, which is one of the roots characteristic equation that are plotted for all the values of system parameters when we change k from 0 to infinity. Again, the root locus is a good implementation, especially when we have a higher order system. This very similar, I mean, when we discuss about Routh-Hurwitz, we used to say we can find the stability for first order, second order, even third order systems in an easy way. We can just find the roots, then we can say the system is stable or not. While if we have higher order systems, then finding the roots, it will not be easy for us. Therefore, we use Routh-Hurwitz to determine the stability. Then the same thing here in root locus. We will use the root locus method in higher order systems instead of substituting the case from 0 to infinity. So the root corresponding to a particular value of the parameters that can be located in the resultant graph. So basically, what we will discuss in the root locus, we will focus on the open loop transfer function. So G of S is the open loop transfer function, and the root locus, we will look at the closed loop or the characteristic equation, which is basically the closed loop, 1 of plus k G of S equals 0, or 1 plus k G H equals 0 if there is a feedback, or if it's a unity feedback, H equal 1. So basically, again, the root characteristic equation, here we will discuss the first thing, the root locus, basically the poles from k equals 0, where it is the system at open loop poles. After that, it's switching toward the closed loop poles. Then again, we will focus the first an open loop transfer function that can be used, which is, again, as I mentioned, G of S. Then from G of S, we will see how the system, how the pole location will be changed by the value of the gain. Here is, assume we have this, let's consider this system. So the closed loop transfer function, which is G of S over 1 plus G A times H. So the characteristic equation, which is the denominator, 1 plus G H, which is equal 0. That's the characteristic equation. Then what we will discuss here is 1 plus G, 1 plus GH equals 0. If we need to do the root locus, we will add the gain K here. As a result, the transfer function will be G or KG over 1 plus KGH. Therefore, the characteristic equation can be represented as 1 plus KGH equals 0. So in order to do the construction of the root locus, basically, we will assume, or to find, when we find the poles, we will assume the characteristic equation equal to 0. 1 plus GH equal to 0. Therefore, G of S times H of S equal to -1. Since it's -1 and we know S is a complex number, which means in polar coordinates, we have G angle G times H angle H equals what? -1, which is basically 1 angle 180 degrees. Then what we can say the magnitude of GH angle G plus H equals 1 angle 180 degrees. So as a result, we can say GH equals to be 1, the magnitude G of S times H of S as a magnitude equal to 1. Then the angle of G plus H equals to 180 degrees, or I would say pi. Sometimes we don't need also to say pi, we can say n times pi. Or I would say 2k plus 1, or 2n plus 1. 2n plus 1 times pi if it is in radian, or 2n plus 1 times k, or times 2n plus 1 times 180 if we are talking about degrees. Because we know -1, it's achieved, which is 1 angle 180 degrees, or 1 angle 180 plus 360 degrees, and so on. So again, we have two conditions, the magnitude condition and the angle condition. So the angle G and H, so any angle G and H, here we said it's multiplied, but as we know the angle can be summed together, then therefore we can say the first condition, the angle condition, G and H -1, or basically, or I'm sorry, let's do it again, which is the angle G and H equals to plus minus 180 degrees 2k plus 1. And the other thing, which is the magnitude, will be G and H equal 1. These two conditions are very important in root locus. I'm sorry, let me fix the point here, this one. This is the first condition. And we have the second condition here. That's when the magnitude and the angle conditions. Let's look at typical root locus plots. Basically, in first order systems, as we discussed in the previous example, when we have 1 or k over, or the overall systems, which is we have k, then here, what do we have is 1 over s plus 1 over tau. Then when we do the closed loop, this is negative, this is positive. Then by changing the values of k's, we will realize that the closed loop poles s equal to negative 1 over tau 1 minus k. So when we start from k equals 0, it will be s equal negative 1 over tau 1. Then if you keep moving, if k equal infinity, this yields s equal to negative infinity. Then it's moving the tendency here. That's the thing. Then how about if we have second order systems? The thing I don't want to do every derivation here because it will take a lot of time, but let's focus more on the concept. So assume in second order system, if we have underdamped situations. In underdamped, I'm sorry, overdamped actually. In overdamped, when we have a two real poles, so basically we have a pole here, then what's happening when we increase the value of k? When k equals 0, the location of the poles are here in the red dots. Then if we keep increasing k, they will be moved to this way. Then this pole is moving here, moving here, moving here, moving here, moving here, until reaching to the point where is the system will be switched from overdamped to be what? A critically damped. So because we will have at that instance, we will have two repeated poles at the same points. So again, by changing the values of k, let me erase it and do it again. When we have k equals 0, the pole's location at the open loop. Then if we are increasing the poles this way, increasing the values of k, the poles are moving from toward this side. This pole is moving toward this side until reaching to the point where the system is switched to be critically damped. Then after that, if we are keeping increasing the values of k's, what's happening? The system will be switched to be underdamped. Then we realize that the system here is switched to be underdamped. Keep going until it goes to the infinity. So k goes to the infinity. It will go up to the first one and the second one go down. Keep in mind, these two poles, when it starts in underdamped, must be conjugate. So which means if we have a pole here, the conjugate must be here. So again, as a result, what's happening when we have underdamped second order system? The first thing, plots the poles like this, location of the poles. Then this one goes here, this one goes here. They will, until reaching to the point, moving from overdamped to critically damped to underdamped. So again, what's happening? The k is not only impact about the stability, it can impact also, since it's changing the location for the pole, it can impact the system behavior. So the system can be moved from overdamped to critically damped to underdamped, depending on the values of k's. So that keep this in mind, that changing the pole location can varies. When we look at this system, again, at that instance, we call it k critically. So this k critically is the value that changes the system behavior from underdamped, from overdamped or critically damped to be underdamped. Or I would say from overdamped to critically damped to underdamped. Then when we observe this, look at the system characteristics. So we will realize that the system characteristic performance is like this, while when we do the underdamped or critically, or if it is here, K lower than critically damped, the lower than K critical, it will be overdamped, or even like critically damped, that's fine. If it is after that, it will start oscillating, which is basically start on the damping, or I would say start the oscillation, or start omega and starts appears, where basically it is called underdamped. So the points when the system switched from overdamped to underdamped, this is the critical way. This is very important result that I need you to think about and keep this in mind. So third order system. Assume if we have a third order system that all of the poles are real numbers. So what's happening? What's the system tendency will be? The overall idea or the overall thoughts, which is basically here is a pole, the second pole, third pole, then the poles will be moving toward a certain rule. How can we conclude that rule? Which is basically start counting the poles and zeros from right to lefts. From right to lefts. Start counting the poles and zeros. So if we get odd number, then we will call it as a Locus region or a Lucy region. If it is even number, then it is non-Lucy region. As an example, in first order system, basically the root locus, or there is one pole, then start counting from here toward here, it is odd. Then what's happening after it? All of it is a Lucy region. Then the next thing, when we do it with the second order, as I mentioned earlier, here, pole, here is a pole, then start counting from left or from right to left. Then basically, here is start counting, here is one, then this is odd, then here is two, this is even. This is a Locus region. So what's the benefit of that? The Lucy region will tell you where is the pole is gonna move. The poles will move toward the region. So what I would say, and when we have a pole here and pole here, they have the tendency to move toward this region until, like I would say, collide, or until reaching the critical points. Then one goes here, the other one goes here. How can we apply this in the third order? When we do the third order system, basically, let's put the poles. Here is a pole, here is a pole, and here is a pole. Start counting from here, from right to left. Then you will see here is number one. So this is odd. Then when we reach at this point, it is now even. Then don't count this region. So when we reach this point now, it is number is 3. This will be odd. Then therefore, it will be taken into consideration until to the infinity. So what we can say is look at the poles. The poles will be moved toward this region. Then we can say the first one, the pole or the left pole, it will be moved toward the region that's associated with it. So it will go toward negative infinity. However, these two poles will be collide or will hit each other, then start going this way, start going this way. So one of the things, the most interesting things, or why are they going, these two poles, I would say P1, P2, P3. So P1, P3, we all agree that it will go toward infinity, negative infinity. P1, P2, they will collide, then it will be switched. But the thing which is, are they gonna switch or collide like this? Or are they gonna collide like this? So here, so far, we will learn this, but not now. So the thing which is, Here we realize it will go like this shape. Okay, that's one thing. Because we have a 3 poles. If we have 2 poles, then they will collide. When they collide, they will go straight. While if we have 3, it will be in angles like 60 degrees. I would say negative 60 degrees and 180 degrees. How can we calculate this? We will discuss this later. How about if we have a third pole, or I would say like a third order systems with 1 pole. So the first thing, let's do the graph. So we have 2 repeated poles. Let me assume, for example, these 2 repeated poles location here. So when we count the numbers, here is P1, P2. Now they are what? This one, P3. When we start counting, these are even. So there is no region. Here, it is start number 3, 1, 2, and there is a third pole. Then this is with the region. Therefore, we will say this is a region, while between P1, P2, and P3, there are not regions because it is odd. Then the pole will be moved to its region. So P3 will be moved to the negative infinity, while P1 and P2, they don't have a region. Therefore, the collide itself is the same as that point. And again, like when we have a double pole, it will be like this. Then what's happening is one will go here, the other one will go here. Again, like 60 and negative 60 degrees, the angle. Then how about when we have the third order with zeros? So when we have a third order systems with zeros, the situation can be kind of different when we have a zeros, because I would say when k equal 0, the pole location is at I would say open loop is at open loop location. Open loop location. While if k equal infinity, the pole location will be moved to either maybe positive infinity, minus infinity, or a 0. So the pole can reach to a 0 at infinity as well. So if we have multiple poles, multiple zeros, then the system can reach again, if we have multiple poles, and maybe 1, 0, or 2, 0, one of the poles will go toward zeros, and the rest will go towards maybe plus or minus infinity, depending on what we have. Assume we have a third order system with 1, 0. So let me do it. Let me do the plots. And remember that let's do the pole 0 mapping first. So assume there's a pole here, 0 here, pole here. Let's determine the regions. Again, the regions are associated with what the counts start counting from right to left. So when we start counting, basically we will say that a odd number or even number. So when we even like the poles, count the poles and the zeros. So start counting from left to right. Let's count here. Basically, the number here is 1. Then since it's odd, therefore it's a region. Then the number here is 1 and 1, 2, which is even. Then since there is not counted, this region is not counted. Don't count this region. Then after what, when we reach this 0, it will be a 3. So this will be counted as odd number. This is a region. So I will count this a region. So again, this is P1, P2, Z1, and P3. So basically start from P1. P1, it is odd, the number of it, then goes, it's a region. Between P1 and P2 is a region. After P2, count the previous poles and zeros, which will be P1 and P2. This is 2. Therefore, it's even. Then the region between P2 and Z1, it's not counted. Then after that, when you start from Z1, the number of poles and zeros are 3, P1, P2, and Z1. This number are 3. Then you can count the area between Z1 and P3. Count this area. So as a result, we have, I would say, like these regions after P3, this region toward the infinity, we have 1, 2, 3, 4 full poles and zeros. Therefore, it is odd region, then it's not counted. So what's happening here? When you look at the region, the pole will go maybe either to infinity or negative infinity, or it can go toward the 0. Look at P3 and Z1. When we started from P3 and Z1, the region from P3 towards Z1, that's the only path between P3 to Z1. Therefore, the pole will move from P3 towards Z1. While P1 and P2, there is no zeros, there are no zeros to go. Therefore, they will move toward opposite of each other until reaching to the critical point. Then from that critical point, they will change. They will go toward positive infinity and negative infinity. So that's how we can figure it out. How about if we have third order with 2 zeros? When we have a third order system with 2 zeros, let me plot it like this. So assume we have, in this example, a triple pole here. 1, 2, 3. We have P1, P2, P3. Then assume we have 2 zeros. Assume there is a 0 right here. Where is it? Here. And another 0 here. Then let's start counting. Here is Z1, Z2. Start counting from right to left. How many poles do we have? How many poles and zeros? From left to right, 3. Therefore, this is counted within the region. Then after that, P1, P2, P3, and Z1, this is 4 poles and zeros. Therefore, the region between Z1 and Z2 is not counted. Then after that, there is a Z2. After Z2, then the total number will be 5. I'm sorry, I have a technical issues, but then we have Z1, Z2, again, P1, P2, P3, that's what we have here. Then after that, this is an odd number, therefore this area, this region is counted. Then when we reach Z4, the total number now is 4. Then this region is not counted. Once we reach Z2, then the total number will be 5. Then this region will be counted. As a result, we can say this region is counted and this region is counted, and this region will be keep going toward the infinity. The poles are allowed to move in the sigma axis or the real axis, only the poles movements at the real axis will be only at this segments. They cannot move in, the poles cannot move here. There is no way. The poles only moving toward the Lucy segment, which is here and here. That's the only way. Now, we would say since we have 3 poles, one of these 3 poles will move toward the 0, the first 0. Then we have 2 poles remaining. These 2 poles remaining, they will be switched. They will be moving like this until reaching to the point where they will also collide. Then one pole will go toward this point, the other pole will go toward negative infinity. So I would say, for example, P1 goes towards Z1, P2 goes toward Z2, P3 will go towards negative infinity. That's the reason why I say the pole location will be moved to either infinity plus minus infinity or toward a 0. So again, construction of the root locus, the first thing is to do the pole 0 mapping. of the open loop. Then after that, try to see how is the system behavior. So here, when we look at it, we will realize in this example, S equals 0, -1, -2. So here is a 0, -1, -2. Then start counting the lossy region. Basically, the lossy region are, which is basically starts to see from left, right to left. This is odd number. Let me call them as P1, P2, P3. When you are at P1, the region is between P1 and P2. Since it's odd number, then this is a region. After P2, it's even, it's not counted. Then at P3, it's an odd number, then it will go toward the negative infinity. Then P1 and P2 will be collapsed or collide, then causing some oscillation. Then will be moved here. Then this one will be moved here. Okay, so again, determine the lossy region in the real axis by start counting how many poles or how many odd poles and zeros goes together. So again, in pole zero mapping, mark the poles X, mark the zeros O, then assume in this example we have poles and zeros, like S equals 0, S equals -4, those are the poles, -2, -4, zeros, I would say no, the poles location again are 0 and -4, while the zeros location is -2. Then if we do the plots, basically, let's do the plotting. We have a pole at 0, pole at -4, then we have at -2. There is a 0. Then start to determine the region from 0 to -2. This is count a region because if you travel from right to left, this is considered as a region. Then after -2, the number of poles and zeros are 2. Then between -2 and 4 is not counted. Then at -4, the number of poles and zeros is 3. Therefore, it is odd. Then start counting. This one will go toward -infinity. Then the 0 will go toward -2. So at the end, when k equals 0, the poles are location at 0 and -4. K equals 0, the poles are location at the poles location at 0, -4. When k equal infinity, the poles location will be at -2 and -infinity. Okay, so that's something that you need to keep in mind. Here's an example of the second order system, or actually, like this is the system that we discussed, determining the lossy areas or lossy segments. Then the next thing is to, when we discussed in the previous example, which is here, how do we know the angle is 60, -60, and 180 degrees? How can I know these angles? Basically, using this formula, which is called the asymptotes lines. So asymptote is the straight line approximated with the curve. It will tell you like about the angle. It will tell you about the angle between the points. And the other thing, it will tell you about the intersection points. I would say here, for example, in this ball, we know that there will be intersects here. So that point of intersection, we'll call it sigma. And the angle of the intersection, we will put like a draw straight lines. So we will say the angle here is psi, and the other angle is -psi. So how can we determine, let's look at this segments. How can we determine the angle and the point of the intersection? Again, here is the pole, here is the pole. Let's look at this segment. We'll look at one pole segment. So basically, this is how the pole moving. We will take the approximate segment. Then this one's called sigma. Then the angle is called psi. So we need to calculate sigma and psi to get an approximate location of the collide of these two poles, the collision. And we will tell you the angle So determine the asymptotes. Basically, in order to find sigma and the angle, is the number of poles, the sum of poles, actually, minus the sum of zeros divided by number of poles minus number of zeros. So sum the poles, sum of the minus sum of the zeros divided by n minus m. Then here 2q plus 1 divided by n minus m times 180. Let's look at this example. In this example, let me draw and see how the root locus looks like. So we have one pole at 0, one pole at -1, and another pole at -2. So I would say the behavior, this is a Lucy segment, or Lucy, and the other one, this one go toward infinity. Then here between 0 and -1, the poles will be collide, then they will travel. But how about the angle, or where is the point of the collision? Then basically, let's count by using the sum of poles minus sum of zeros dividing by the number of poles minus number of zeros. So the sum of poles, basically, we have a pole at 0, pole at -1, pole at -2. The sum of zeros, we didn't have zeros, divide by 3, 3 poles minus zeros. So which is basically, this yields to be -1. This does not mean they will start collision at -1, but I would say the asymptotes of it will go at -1. However, in order to calculate, the angle will be 2q plus 1 divided by n minus m, such that q 0, 1, 2, until the poles number. So we will start determining, substitute q0, substitute q1, q2, when we have 3 poles. If we have 4 poles, substitute q equal 3, then 4. So which is pole numbers minus 1. If we have 10 poles, we will say q equals 0, 1, 2, until 9. If we have 3 poles, we will say q equals 0, 1, 2, and so on. That's how we stop, or how we substitute q. So basically, 2q plus 1 divided by n minus m, which is number of poles minus number of zeros. So it will be 2q plus 1 divided by 3 minus 0. Now, let's substitute q as 0. This yields to be 1, on here, don't forget, times 180. 1 over 3 times 180, which will be 60 degrees. Then q equal 1. This will be 3 divided by 3 times 180, which will be 180. Then if you q equal 2, this is the last one, 2 over 3, or actually 2 times 2, 4, 5 over 3, which is 5 over 3 times 180. This will be 300, or in other words, negative 60 degrees, okay? Then, since we got these 3 angles, negative 60, 180, negative 60, let's look at the poles. We can say this pole, or -2 pole, since it's allowed to move only to the left, this angle is 180 degrees, and that's fine. How about 0 and -1? One of them will go with angle positive 60, and the asymptotes at -1, positive 60, the other one at -60. Those are the asymptotes. How about the behavior? They will be moving like with a point, intersection point here, like this, like this. Okay? Here, it will give you a clear image, and the reason why these poles are moving this way, not moving straight. How about if we assume we have a second order system? Here, again, this is the angles. This is how it looks like. Assume we have a second order system, like 1 over s plus 1, s plus 2. So when we put the poles, here is -1, here is -2, then they will, of course, this is the only Lucy region segments. Then in this segment, basically, they will go with different angles. So the first thing is to determine sigma, which is number of poles, sum of poles minus sum of zeros, over number of poles minus number of zeros. So which will be -2 and -1 divided by 2, which will be -3 divided by 2, which is -1/2. This is sigma 1 minus 1/2. How about the angle psi, which is basically 2q plus 1 divided by n minus m, or is it n plus m? Let me check. N minus m, full minus zeros, times 180. This yields 2q plus 1 divided by 2. Substitute q equal 0, then it will be times 180. It will be 90 degrees. Substitute q as 1. This yields to be 270 degrees, or in other words, -90 degrees. And then that's it. Don't substitute q equal 3 because we are done with 2 poles. Then basically we say the segment at -1/2 and plus 90 degrees minus 90 degrees. Then this is 1/2 minus 1/2. Then this is the point where the pole will go with positive 90 degrees, negative 90 degrees. And that's it. That's how we determine the angles. Why these poles goes as a straight line, or why this goes with 60 degrees or -60 degrees angle. So that's what I want you to understand. Here is a homework for you. Let's try to find the root locus angle asymptotes, centroid asymptotes. So we will stop here, then we will continue next lecture.